Hi, and welcome to this series of lectures introducing compressible flow theory. So here are the Navier-Stokes equations I've been showing a lot, and in general, I have rearranged these or included them such that they include the compressible effect. So this is the compressible conservation of mass equation, and this is the compressible momentum equation, even though you got this term out here. It is the compressible form because we simplified it using the conservation of mass, if you recall. And then this is a form of the compressible energy equation, and sometimes we'll use the Boise-Nask approximations, but that's a general form right there just to get us started. So the objective of this series of lectures lays out the foundation for compressible flow relations. And over the next couple of lectures, we're going to derive the polytropic isentropic flow relations and develop a relationship for the sound speed of air, sound speed of gases, I should say, and the Mach number relationship and what it means. We're going to develop the Mach number relationships, meaning the isentropic flow relationships in terms of the Mach number. And we're going to look at converging, diverging nozzles and the special considerations for those flows, develop Fano curves and Rayleigh lines, and eventually get into the Rankine-Hugoniot jump conditions. Now, in this set of lectures, we're just going to maybe tackle two of those, derive the polytropic and isentropic flow relationships, and develop a relationship for the sound speed. All right, so let's get going. Isentropic processes. So let's start with Gibbs equations, or the TDS equations, sometimes called the second law. These go by a lot of different names. And it's a relationship between the heat transfer in terms of the entropy and the internal energy and the PDV work. And so if we are to assume that this is an isentropic process, then ds will be 0. There will be no change in the entropy. So that term and that term will be 0. And then we'll just be left with the internal energy as a change of minus PDV, which is that PDV work. All right, so if we now insert the ideal gas relationships, you get PV equals MRT, or P over specific volume times RT. And then we're also going to make the perfect gas assumption. And so the perfect gas assumption is one better than ideal gas, right? So this is the ideal gas relationship, and a perfect gas is really this relationship right here. So notice I took d by dt of both sides of this and rearranged, and I pulled this v out. So I'm not taking the derivative of v with respect to t, so that means it must be a constant, and that is the perfect gas assumption, that the specific heat is a constant with respect to temperature. Now, that's not necessarily always true. Here's an example of what the temperature curve, and this is the specific heat on this axis, and here it is, and here's these guys right here. Those are your noble gases, right? Those gases where the valence shell is full of electrons, so they have no repulsive or attractive forces due to the Coulomb forces, but also because they're single atoms, they also don't have any vibration or rotational degrees of freedom, so they don't absorb any more energy in those modes. Now, notice here's your diatomics right here and your triatomics. So each one of these kind of bunches together as we move up, and the complexity of the molecule to absorb energy in vibration and rotation modes. And notice air is part of this set because air is just composed of multiple diatomic molecules. Anyway, back to our derivation. So if we combine this and this and this together, we get a relationship like that. And then if I rearrange this, you can see that I've really got d by dt equals dv by v. So that's ready to go, ready to integrate, because this r over cv we're assuming is a constant. So that's easily integratable. And when we do, we get ln of t plus r over cv ln of v. And that's equal to some constant because I didn't integrate over a given limit. So I did an indefinite integral there. So here I just rewrote it, and I employed the little trick here with regard to logarithms. I just took the exp of both sides and got this here where I've got some new constant now, C2, right? Now, let's recall those ideal gas relationships, that C sub P minus CV is equal to R, that the ratio of Cp over Cv is equal to gamma or K, and that guy's got to be bigger than 1, right? Because Cv is always bigger than, Cp is always bigger than Cp. Cp is always bigger than Cv. It always takes more heat to increase the temperature by 1 degree in a piston-cylinder arrangement where you have to lift that piston in addition than it would be to increase the temperature by 1 degree in a rigid box where you don't have to do that additional work. So Cp over Cv is always greater than 1, and for a solid material, it is equal to 1 for incompressible limit. Anyway, we're doing gases, compressible. Finally, we've got the ideal gas relationship. If I combine those first two there, I get that the ratio of R over Cv is really equal to the ratio of specific heats minus 1. So that can go right in there and help me simplify that out. So if I do that, if I insert this guy in there, and I put in that gamma minus 1 is equal to R over Cv, I get this. And you can see that this is going to cancel that. And then R is a constant, so I can just throw it into that constant. And so really, I get that P over rho to the K, I just move that V downstairs, is equal to some constant, right? That would be C2 times R. Now, to get to this, I needed to invoke the isentropic relationship and the perfect gas relationship. So keep that in mind. Together, this is called a polytropic process. All right, so if it's equal to a constant, if P over rho is equal to a constant at a given state, then it must be equal to the same constant at some other state, right? So I can make this relationship between states that P1 and P2 are related in that way. Now, from this and the other ideal gas relationships, we can generate a whole series of isentropic relationships. So here they are, and I challenge you to see if you can't derive all of these. It's not very hard to do. I'd give this a 1 bean sort of difficulty. But yeah, go ahead and try it. It will polish up your skills here for the isentropic relationships, which we're going to use a lot in this module. All right, let's talk about Mach number. So here's maybe our hero for today, Ernst Mach, a bit of a character. This is when he lived, and he spent most of his time at University of Vienna with Schrodinger, actually. But we're familiar with Mach number. Mach number is the ratio of the local velocity to the local sound speed, A. That's what we're going to call it. Now, before we go too much further, we should credit Mach. This is the first photograph that Mach took and that anyone had ever seen. This is the first photograph showing a shock wave in 1887. So that's pretty amazing here. There's a tripwire or something here with a bullet going by, and you can see the bow shock. You can see the turbulent wake. It's a beautiful photograph. Hey, he got a stamp named after him. I mean, that means he arrived, right? And as a note, I worked at the Fraunhofer Institute for Kurzzeit Dynamics. That means short-time dynamics. The Institute for Short-Time Dynamics, it's named after Mach, so it's the Ernst Mach Institute. Ernst, by the way, in German means serious. So like in Harry Potter, you had that Sirius Black character. His name would be Sirius Mach. That's kind of fun. And he was apparently a pretty serious guy. So this was a self-portrait by Mach, which is pretty fun. It is a self-portrait from the perspective of the artist, right? Here's the top of his eye there. There's his nose. He's looking at his left eye, and he's looking at himself reclining on a couch. There's his hand, and he's drawing himself. So, I mean, come on. You got to love that, right? Anyway, let's talk about Mach number. So what is the sound speed for a perfect gas? Can we derive it? And it's a good question, and it's stumped a lot of people for a long time, including Newton. So let's go through today's accepted derivation of the local sound speed. So we want to get this guy right here so that we can form Mach number down the road. All right, so the characteristics of a sound wave is that they're really mechanical waves that transport disturbances or information from one location to another, not amp4, but one location to another at a finite speed, right? So things happen at a finite speed, so information travels at a finite speed. They're produced by vibrations and organizing waves, and this sound wave is a packet via molecular interactions, really. It exists at the molecular scale, one molecule bumping into another, and so forth. Let me ask you a question, a little quick espresso shot. You don't have to say it out loud right now so no one else can hear you. But how do sound waves affect the temperature of air? So you're listening to me probably on a computer, and the sound is coming out of the computer and it's propagating through the air to your ear. Is it heating the air? Is it increasing the temperature? More to the point, is it an adiabatic increase in temperature or not? So let's go over some of that, right? If it's adiabatic, that means that it can increase the temperature, but this sound wave goes so quickly that it quickly drops back down, so that effectively over time there's no residual temperature in the gas, right? So the sound wave goes by very quickly. It raises it and it lowers it. There's not enough time for the heat to dissipate away, so that's the adiabatic assumption. What about, is it isothermal, that this wave goes over it and it just doesn't heat it, significantly at all? What is that? So, pick your favorite candidate. You really got three: adiabatic, or it increases the temperature and it permanently is increased. It's adiabatic when it rises and it falls, or it's isothermal. So just jot it down, and we'll go through this and we'll see where you come out on the other end. All right. Speed of sound. So here it is. Here's a sound wave. It's propagating along at a speed a, right? And the derivation, we're going to use a control volume approach, and you're going to be the observer, and you're going to be standing on the sound wave. So if you were standing on the sound wave, riding along with it, the sound wave would look like it's stationary to you. But what would be happening is it would look like the air in front of you is flowing into your control volume, right? So really, it's just a little transformation here, Lagrangian Eulerian transformation. So you have this inlet air flowing into the control volume, and it comes out the backside. If you look back there, you can see the air coming out, and it would be some different velocity, right? We're saying some small change in velocity, and we could have put the small change on the front or the back. It doesn't really matter, but we did it like this with our sign convention minus dA. All right, so really, you have a whole series of states. This air, it's as if this air is going into this control volume, carrying with it a pressure, a temperature, and a density, and it's popping out the other side with a slight change in pressure, density, and temperature, almost like a Taylor series expansion. Let's assume 1D flow. So all of these are going to be properties of just X. Let's also assume steady flow, which isn't hard to swallow. So here's our image over here on the right. Let's keep this guy in mind as we move forward. So let's start with conservation of mass. 1D flow, steady. So if we write the Reynolds transport equations, there they are. And I've, for emphasis, wrote this rho dx and v dx, that's the velocity, dotted with some unit normal that's normal to the dy dz plane. First thing we're going to do is make it steady, so we get rid of that term. And in our control volume, we have one inlet and one outlet. So we're going to have an in and an out. And notice I wrote them as one-dimensional steady. Now, how do I justify that? The way to justify it is that you recognize that this rho is some function only of x, right? So it can change. Maybe the density increases as it moves through the x coordinate. And this integral here, right, dy dx, is in the dy dz plane. And so this can be, these guys can be functions of x and still be pulled out of the integral. And so that's what we've done here. We've pulled them out of the integral. The integral of just the area gives us just area. So we've got rho VA equals rho VA, even though they vary with space and are compressible in the x direction only. All right, So we then insert the states, right? So on the inlet side, this guy right here, you just have P times A. The density is rho, the velocity is A, and the area is A. The area, this is the area here of the control volume, right? Now on the outlet side, the density has changed, rho plus d rho, so that's that. And then the velocity, we just assumed it to be A minus dA, so there's the velocity. And because I drew a square control volume, the area on the back side is just A as well, the same as the area on the front side. So the constant areas will cancel out. And if I FOIL this, if I multiply this out, I'll get something like this here. And notice that we're going to make this assumption that the product of small numbers, dA, is going to be dA times d rho. Since dA and d rho are both considered small, when you multiply them together, they're much smaller than, say, A times d rho or just rho times dA, so we'll get rid of it relative to those other two terms. So we really end up with a conservation of mass relationship that simplifies just down to this little differential relationship there. All right, let's do the same for conservation of momentum. So again, here is our Rayleigh transport equation in all of its glory, and if we make it steady, we'll get rid of that term, and then we'll just insert our velocity and our m dot into our two flux terms and get this here. And then we'll recognize that the only loads on this control volume that we have are just the pressure loads. So you've got a pressure acting inwardly normal on the right side and inwardly normal on the left side. So there's a change of sign here. So P plus dP times A plus P times A. And then you can see those guys will cancel out. And we'll do the same thing with the momentums, right? So all of the outlet momentums have the dA in it, and all of the inlets are just the state variable. So the constant area allows us to cancel out the pressures, and if we FOIL all this out and you make the same assumptions about products of differentials being small, you'll end up with just this simple equation here. We can do the same with conservation of energy. There's the first law in steady flow. And if we assume adiabatic and we assume no work, then, and we get rid of the potential energy terms, then we're just down to this guy right here. And again, we've put in the H plus DH, and the A should be minus dA. And if we FOIL all of that out and cancel out the products of small numbers, we'll get this guy right here. All right. So if we combine the mass and momentum equations, there they are. We combine those two, we'll get dP equals A squared d rho. We rearrange that to this little differential. A squared, the sound speed squared, is equal to the derivative of P with respect to rho. And I put the isentropic subscript S there because we did have to assume that it's frictionless. We had no other forces acting on our momentum equation. Back here, we just had pressure, no friction or shear stress. And we also assumed that it's adiabatic. So together, right, those two make it isentropic. So we're just tipping our hat to the isentropic assumption there. Now, previously, we just had this isentropic relationship for P over rho to the K is equal to a constant. So that's perfect. That's what we need. We'll put that guy in there, and we'll take the derivative of that. So we'll insert that in there. There it is, some constant. That's the constant there, times rho times, look at that, I switched from K to gamma for no good reason. And I take the derivative of that, and it's pretty obvious that's what it is. And then you can see I can just combine this back and get rid of this constant. That's clever. So the constant times this rho gamma will give me just this relationship here. You can see that. And if I use PV equals MRT, I can get it to look like that. And so finally, I get this resulting sound speed after all of this. as being A is equal to the square root of gamma RT. Very famous relationship. A is equal to the square root of the ratio of specific heats times gas constant times T. Great. So we can use that moving forward. Now, let's have a little bit of a history, a little bit of a story here. Here's Newton. Newton lived here in this time frame, 1642 to 1727. And it's often quoted that Newton, back when I asked that espresso shot question, I said, did you think it was isothermal or adiabatic? And so the story goes that Newton assumed that it was isothermal and went down the path of isothermal. And if you do that, you can quickly show that if I put in P from PV equals, or P rho equals RT, so this is the ideal gas relationship, and I assume T is equal to a constant and R is equal to a constant, then I can easily pull those guys out and then just take the derivative with respect to rho and you get RT, for constant temperature, mind you. So you don't need that isentropic relationship. Now, if you do that, you get the sound speed is equal to square root of RT, and that's going to be wrong because there's no gamma in there. It's wrong by the square root of gamma. And for air, gamma being about 1.4, that's about 18% error, as you can see. So that's a common story that Newton assumed isothermal, and he ended up with the wrong relationship. Here it is. Here's a quote even from Wiki, right? He neglected the effects of fluctuating temperature that was later rectified by Laplace. Of course it was Laplace that later rectified it. That makes a great story. But when you sit around and you think about it for a second, you're like, hang on, 1687? So Newton had just proposed calculus, which we used a ton of in that derivation. Also, the whole ideal gas relationship was unknown to Newton. PV equals MRT wasn't really flushed out till about the 1830s, right, from Boyle's law and Charles' law. So there's no way you could have known that. And further, the whole perfect gas thing, this was still in the era of the caloric, right? So if you know anything about the history of thermodynamics, people thought that heat was like a fluid that was stored inside of matter, and it flowed like a fluid from one body to another. So if you put a cold body next to a hot body, you put them together, this caloric would flow from one to the other, this heat. They didn't realize it was just the vibrations of the molecules. There was no substance to the heat itself. It was just energy. So that was still, a pretty big theory even in the 1750s when Newton was around. So if you think about it, there's no way he made that mistake, right? None of this mechanism even existed in his lifetime. So it's a better story to ask, well, how the heck did he even figure out what the sound speed of gas is? And in order to do that, we have to go back to the first source and read Newton's ideas himself. So if you go back and you read his paper, he really started with Galileo's idea here. Now, Galileo had preceded Newton, 1602, and he was goofing off in church one day, and he was looking at the chandeliers hanging from long, long chains of these cathedrals, and noticed that they would swing. And even today, right, you can go into church and you can see these guys here a little bit swinging. And he noticed that the period of all the chandeliers was the same. And the period, meaning how long it takes for it to go back and forth one time, is the relationship 2 pi over times the square root of L, the length of the pendulum, divided by G. And this is a fabulously accurate equation developed by Galileo. Now Newton, he came along and he said, you know what, I can use this to calculate the sound speed in air. I'll assume that a perturbation or a disturbance is like a pendulum swinging, that the sound is like a pendulum swinging. How long should the pendulum be? Well, it should be as big as the atmosphere, however tall the Earth's atmosphere is, the air. All right, so he needed to calculate this length L. And he did that by using hydrostatics, which was also known at the time. This was a Greek thing, right? What's his name there? Archimedes had developed hydrostatic. So the atmospheric pressure, which he measured with a manometer, a mercury manometer, rho times GH, is equal to the air pressure, rho times GH. So he equated those two, and he knew what the, if you read this, they called mercury quicksilver back then. He knew what the ratio of specific heats of mercury was, 1,890 to 1, the ratio of air to specific heat of specific gravity of mercury. So he solved for that. 30 inches of mercury he measured as the atmospheric pressure divided by the ratio of specific heats. So you multiply by that number there, and he got that the Earth's atmosphere is 29,000 feet. And we know that to be a little bit short, right? Planes fly at about 29,000 feet. So really there's a gradient of density he didn't account for there. He should have integrated. Come on, dude. But he got 29,000 feet, and he used that in his L there to calculate that the period of a pendulum that's 29,000 feet long, the perturbation in air, it would take about 190 seconds to do one cycle. And knowing what the circumference of this pendulum is 2 pi r divided by 190 seconds, he got 979 feet per second. The actual sound speed and standard temperature pressure is about 1,025 feet per second. And you know, this was a military secret, so to speak, at the time, because if you knew what the sound speed of air was, you could know, if you saw your enemy fire a cannon at you, you would know how far they were by the delay in the, when you saw the cannon fire and when you heard the cannon fire. You could measure that delay time, which would be related to the sound speed, and then you'd know exactly how far away they were, and you could take your pre-calibrated cannon and crank it to hit that distance. So that was quite the military advantage, to know the sound speed in air very accurately for a given day. All right. So interestingly enough, this factor is off of that factor by about this 18%. It's really about 15%. And it bothered Newton. And so this book here, this is actually the second edition. Newton had 2 editions of this. This is Principia, by the way, that you're looking at here. And in Principia, he went on to say, well, it's the dust in the air, right? He knew his estimate was low. So he said, well, the dust is increasing the air, and so is the water in the air. Those two things, the dust and the water, are increasing the sound speed by, and he went on to estimate it and get it a little closer. So he was embarrassed even in his day, and people continue to rail him. But I find it better to actually read what he did than to have him say that he assumed it was isothermal. That's crazy. All right, interpretations of Mach number. So here's an airplane, and you can think of sound emitting from the airplane in all directions. And if the airplane is stopped, sitting on the tarmac, then we're getting information going in all directions. And as it moves faster, right, it's definitely going to Doppler shift this air a little bit. And as we approach the sound speed, really the nose of the airplane is reaching the threshold of how fast information is getting out of the way, or is being propagated forward. So eventually, at supersonic speeds, the molecule, which would typically get a signal from the coming plane via the sound speed, hey, something's coming, you better start getting out of the way. When you get to sound speeds of 1 and greater, that molecule doesn't have a chance to get out of the way. The information isn't propagating back upstream, and so you form kind of this cone of influence, right? It's really a cone of silence where information is not crossing across that cone until much later, until after the plane passes. So this is akin to, you know, everybody's in a crowded theater and somebody yells fire, and all the people get up and they go rushing out of the theater, and then there's a jam up at the door. Only so many people can get out of the door, can flux through that door at a given time. And so everyone's pushing in the back, and this information that you can't get through isn't propagating back to the people to stop pushing. They just keep on pushing, and it creates a real problem, as we know. So a similar sort of interpretation to this pressure wave domain of influence interpretation. And another interpretation that I really like, I'll call it interpretation of Mach number 2, is from Charlie Anderson's book, not Charlie Anderson, John Anderson's book. And it really has to do with that the Mach number is related to the ratio of kinetic energy to internal energy. So we know kinetic energy to be 1/2 rho v squared, and internal energy, let's just call it U. That's kind of our classic thermodynamic variable. So we could write U as CVT, right? Now I know that CV is equal to R over gamma minus 1. You would have found that out if you tried the coffee break. And so I can substitute that in there and get this gamma minus 1 in the numerator. Now, I know, too, that the sound speed is gamma RT equals A squared. So I can put that in for this guy right here, that RT is equal to A squared. Now, look what I got going on here. I got V squared over A squared. So I can collect that together, and I get Mach number. And this is just a bunch of constants here, right? So it says then that the energy over the internal energy is really a definition of just the Mach number. Thus, the Mach number is related to these two. And that this is really a measure of the directed flow. That's what this kinetic energy is, this organized motion of gas compared to, or divided by, the random motion of gas, the translational components within gas. So as this organization exceeds this randomness, then you have Mach numbers greater than 1. That's a really cool interpretation of what the Mach number is. Anyway, let's wrap this up. We derived the polytropic relationships and the isentropic flow relationships, and we developed the sound speed, so we have a good foundation to move forward. And next time we'll talk about isentropic flow through variable area nozzles, whereas here we just had that square control volume. So until next time, I hope you try the coffee break, and I'll see you later.